Hello, this is section 2.9, talking a little bit about formal charges and resonance structures. So your book goes through a very small section about formal charges, and I just want to clarify a couple points because I don't really prefer how they explain it in some instances. So if you remember from the last section's video, we talked a little bit about curved arrows and resonance forms. So we had this example of an amide functional group. And in this amide functional group, we had a good arrow that went from the amide's lone pair to the bond between the nitrogen and the carbon, and then arrows had to then flow from the bond between the carbon and the oxygen up to the oxygen atom. Because if we didn't do that second arrow, then we would be left with 5 bonds of carbon, which is prohibited, which is totally a bad structure. So what that would leave us with is the following structure. And we learned from chapter 1 that it's always important to know the formal charge of any atoms that we're using. So here, the formal charge of this carbon is 0. I forgot this carbon over here. The formal charge of this one is 0, and this one is 0 too, as well as this one. So all the carbons have a formal charge of 0, and if you're unsure why, please go back and look at the section on calculating formal charge, which is section 1.4, and the section in 2.3, which is identifying formal charges um, in bond line structures. Now, oh wait, that's not 2.3. It is 2.4. Right, sorry, 2.4. Identifying carbon atoms or identifying formal charges on carbon. Okay, so let's look at the nitrogen and the oxygen. If we remember our formal charge calculation equation, nitrogen here has 5 valence, so formal charge equals the valence, which is 5, minus the non-bonding electrons, which is 0, minus the number of bonding electrons, 8 over 2, which is equal to 5 minus 4 is equal to plus 1. So it has a charge of plus 1. And the oxygen has a charge of negative 1. If you're unsure as to why it's negative 1, please do the same formal charge calculation there for yourself. Now, it's very important when you're using resonance structures to keep track of what the charges are on each of the molecules, because if you can do that, later on in this chapter, when we talk about distinguishing which resonance structures are better than others, you'll have a jump on that particular set of information. Okay, so your book mostly ends it there. They tell you this is kind of all there is to know. Just be careful. There are charges. One thing they do say that I don't like, and I want to tell you right now, is that in your book, they say that this kind of movement is allowed. So in your book, they have a minus charge on an oxygen, and they take an arrow from that minus charge down to this bond, and they move this one, that bond, onto an atom. But this is bad because they don't actually tell you which lone pair does the movement. Because if you remember, that oxygen has 3 pairs of electrons, right? And so if you just say it's the negatively charged pair, you don't actually know which pair it is that makes the negative charge. And that will be counted wrong in this class because it is not good electron accounting, nor is it very rigorous science. So what I would prefer you to do instead is draw in those lone pairs whenever you have a negative charge. That way you can say which lone pair is moving. Okay, so remember, not this type of structure. This one is good. All right. So let's work one quick example and be able to draw a resonance structure and keep the charges. So here we have this type of molecule, which is called an allyl cation. This functional group is an allyl group, and there's a cation on it, so it's an allyl cation. Now, we can do a resonance structure where we move this pair of electrons here to give us this structure. And we can do that because if you remember, when we looked at carbocations, we said that the positive charge is actually in a p orbital, remember? And we said that that is the better indication of where the positive charge actually is. So if you have a positively charged p orbital, and you also have p orbitals from this pi bond, then that means the positively charged, the carbon with the positively charged section can also participate in this pi bonded network called conjugation, and we can do the resonance. We can use resonance to move those electrons from one part to the other of this molecule. Okay, one more, just for good measure. Let's say that we have this molecule. Here, this is another planar molecule. This ring here, circled in orange, is called a benzene. It's a six-membered ring that is totally flat because of its alternating, let me draw these a little better, double bonds here. There we are. And since it's totally flat, it also makes this nitrogen want to be totally flat. And the reason why is because if it's totally flat, this this lone pair of electrons here can participate in the conjugation of the molecule and make resonance forms like this. And this type of phenomenon is something that we'll cover in section, what is that? Section 2.13 on delocalized lone pairs. There we go, we got our charges in there. All right, and this is section 2.9.